Good afternoon.
Hello guys, nice to see you. Hi. So, how are you doing? Are you planning to complain on how difficult was the midterm? Hello, good afternoon.
Good afternoon. Nice to see you.
Yeah, glad to see you too.
Good afternoon.
Hi. Okay, so let's start from some comments on the midterm. There's some question. Yeah, sure, that is necessary to try to be like very attentive, specifically not losing point for mistakes which could easily be avoided. So as I mentioned before, there should be different like problems with different level of complexity, and obviously in order to adequately give a chance to students to reveal their knowledge in the material, that should be quite a wide range. And there is a question. Hold on a second. The last question. We need to look there, because there's another, it's a question what is asked also is either like vector quantity or scalar quantity, but we will take a look there also. So probably you can send me email with this comment and your vision of the situation. We can consider this. So we need to take into account that in any way it will be normalized per average performance. And yeah, hello. And then based on that, it will have, after normalization, have impact on your final grade, which will obviously be also normalized to performance, average performance of all students within this year. So it's not a problem if you like solve less than, let's say, 50% of the tasks. It still doesn't mean that you, for current stage, don't pass. It all will be defined by the average performance of all students. And I think that's an appropriate approach to evaluate. It just gives a chance for very strong students to be above average, and other students still pass, because if we make very simple problems for the midterm, that obviously wouldn't be the case, and that's impossible to do like that. So I think in general it was okay-ish. Of course, could have been better, obviously. There were at least 3 problems which were quite simple. I'm sure a majority of you could have easily solved them, but probably some stress and lack of time. But again, follow this concept. try to find those simple problems and solve them first, so you are done with simple tasks and then can proceed with more difficult. But in general, I think that's everything is going okay. Just, I believe that with some experience and for next midterms and final exam, it will be already more accustomed for you, and it will go better. Okay, guys, so we start a new topic this week, and this is linear momentum and conservation of linear momentum. Very important topic in the course of mechanics. So today we are going to introduce the concept of linear momentum and show that for a closed or a quasi-closed system where forces are not acting, external forces are not acting, or they are compensated, there is conservation of linear momentum, and that could be a very neat approach to solve different problems when we can use this conservation of linear momentum. Okay, so now I think we can switch to the slides where you can write and proceed with our new topic. So in order to introduce linear momentum, I think let's consider a situation like simple one with constant force applied, and then according to second law of motion, m times f is equal m times a, we will get some constant acceleration of the body to which this constant force applied, and that can be represented as v2, like final minus initial v1 velocity divided by delta t. So now let us substitute this expression for A here. Will be constant force is equal to m times v2 minus v1 divided by delta t. So if we rearrange delta t to the left side, here will be f times delta t is equal to m v2 minus v1. So here in the left side, this is so-called impulse of the force F, and defined as product of force and time duration during which this force is acting on the body. And here we can write it in different terms. It's actually P2 vector minus P1 vector. So this is difference in of linear momentum. So it's equal to delta P. So in general, we can write that linear momentum is a vector quantity. It's equal to mass times velocity vector. And so linear momentum and velocity vector, like velocities, they have the same orientation, but the magnitude will be defined also by the mass of the object and velocity, obviously. So the units for linear momentum will be kilograms times meter over second. So it's mass times velocity, meters per second. And now let's write finally, like in a short form, that our force impulse F times delta T is equal to delta T change. Impulse of the force is equal to the change of linear momentum. Now, if we consider very short time interval, let's say we have limit delta T is approaching 0, then we can get for the force definition as derivative. So it can be defined as derivative of linear momentum vector over time dp over dt. So if we substitute here expression for the momentum, linear momentum, it will be m times dv over dt, which is actually m times acceleration. This, so far, we were considering only for the case when force was constant. However, that could be the case when force is a function of time. So if we have this situation, then change in the linear momentum, the delta p vector, is equal to some average force times delta t. So this is average force during this time interval delta t. In order to get this average force, average is equal, so it's general definition of how we get some average value of a function of some independent variable. So in this particular case, independent variable is is time. So here is 1 divided by t2 minus t1. So difference, like time interval here in denominator, times integral from t1 to t2. Here is our function, f as a function of time, dt. So this is the general approach how we get average value of the function within some interval of where the independent variable is changing. In this case, it's t1 and t2. Then we can apply this average force in order to calculate change in the linear momentum. So at this stage, we introduced what is linear momentum. We have shown that there is a relationship between the impulse of the force and change in linear momentum. And also, like I've shown that the force can be defined as the derivative of linear momentum over time. And also highlighted that in case of time-dependent force, we need to operate with some average force during time interval in order to get change in the linear momentum. So now let us go to next step and show that in some particular cases, means for a closed or quasi-closed system, when external forces are not acting on the system or they are compensated, we can get conservation of, can show that conservation of linear momentum works, and that could be a nice concept which can be applied to some real conditions under some restrictions, which we will also consider. So now we consider ideal isolated like closed system. So first stage, we have two bodies, M1 and M2, moving in the same direction, but with different velocities, V1 and V2. Let's assume that V1 is larger than V2. That means automatically that at some point, these bodies will collide. So this process of collision is not an instantaneous process. It will take some time. So the forces, the interaction between these two bodies will first increase, reach some maximum, and then decrease over this duration of the body. So it will, the body M1 will reach body M2, and the maximum of interaction will happen, and then they will detach. So that will also be the process of reduction of this interaction between two bodies. But what we can for sure write, that doesn't matter what, in any moment of time, the interaction, like forces between these two bodies, let's say we have F1 will be the force exerted on body M1 by body M2, and here is force F2, which will be exerted on body M2 from the side of M1. They will be, according to third law of motion, in any moment of time during this collision, during this interaction, they will be equal in magnitude and different, like opposite in direction. So this we keep in mind, because this will be important further. And then third stage of this situation, after collision, these bodies, we consider that they continue moving in the same direction. This is M1, this is M2, but their velocity vectors obviously will change. So it will be V1 prime vector. It's some new velocity of body M1, and after collision, and will be V2 prime vector. Okay, so now let us proceed to some quantitative analysis of this situation. And we can write for very short interval of time, some instantaneous time moment, when we consider that these forces are equal during the collision. We can write that F1 vector times delta dt is equal to dp1. So impulse of the force F1 during this moment, instantaneous moment of interaction, will be equal to like very small change of linear momentum of first body. Then we can write for the second body the same equation, will be dp2. Here we have vectors. And let us now sum up this. So it will be F1 plus F2 times dt equal to dp1 plus dp2. So we already mentioned that at any instant of time, these vectors are equal by magnitude and opposite in direction. So if we sum them, they will result in 0. So I would like to highlight again that these forces F1 and F2, they will change during the collision. So they will not be constant, but at any instant of time, this is valid because of third law of motion. So for any instant of time, the sum of these two vectors will be equal to 0. So we can write that dp1 plus dp2 is equal to 0. So if we operate with like very small changes in linear momentum, here vectors, then in order to get total change of linear momentum because of collision, we need to integrate. So if we consider that collision starts at time 0 and ends at time after like time interval delta t, so we can go for integral from 0 to delta t dp1 plus integral from 0 to delta t dp2. And this will also be equal 0 because integration is actually summing up. And if we sum up some small during some changes of the sum of this vector p1 and p2 during small intervals of time, which are equal to 0, if we sum up many of these 0 changes along long interval of time delta t, that will not change anything, and eventually we will get also 0. If we add 0 to like many times, it will eventually be 0 in any way. So taking this into account, we can rewrite this form in a bit different, this equation in a bit different form. So it can be written as delta P1, like total change of the linear momentum of first body, plus delta P2, total change of the linear momentum of second body because of collision, will be equal to 0. So let us go to another slide. Let's write it here. dp1 plus dp2 is equal to 0. So, and that this change, total change of linear momentum vectors can be represented as follows. So it will be, we remember, let's take a look here, that after, so before collision, it was V1, and after collision, it's V1 prime. The same stands for the second body, V2 before collision and V2 prime after collision. So then we can write that P1 prime, so linear momentum after collision, minus P1 linear momentum before collision. So this is for first body, plus P2 prime minus P2 is equal to 0. And from here, if we rearrange it, we will get the following. It will be P1 plus P2. So the sum of initial linear momentum vectors of the body 1 and 2 is equal to the sum of final linear momentum vectors, which is P1 prime plus P2 prime. And that is constant. because we had it before collision, this is after collision, and this doesn't change. So it stays constant. So it actually shows us that for this closed system where there are no external forces, we get valid conditions for realization of conservation of linear momentum. So this is valid. So this we have shown for the system of two bodies. So if there are some systems, closed systems with many bodies, we can write that the sum I from 1 to n, how many bodies we have in this closed system, of all linear momentum, like sum of all linear momentum, will be equal to constant. And this is very useful for different applications. However, we need to highlight that closed system is some ideal approximation. So obviously there are always some forces acting on the bodies, and the most common force is gravitational force. So there is some weight of bodies. However, for some cases, these systems can be considered as quasi-closed, and the concept of conservation of linear momentum can be applied. So let us consider these three most common cases when we can apply a law of conservation of linear momentum. So first one is when we have two bodies, they have some weight m1g, then m2g, and some reaction of the surface on which these bodies reside. So it's n1, n2. So in this case, it's not closed system because we have weight of these bodies. However, this weight is compensated by reaction of the surface on which these bodies are located. So if we consider some frictionless case, there is no friction between these bodies and the surface, then this system is good enough as a quasi-closed system for application of conservation of linear momentum. So second case is when external forces which act on the system are much smaller than internal forces. And very good example here is when we have some explosion. So we have projectile which explodes, and during explosion it's very short process, like very fast process during short interval of time. So external forces for this particular example will be weight of the projectile which explodes. However, it will be much smaller than the internal forces which cause the explosion or which evolve during the explosion process. If this is true, then with quite good approximation, we can apply law of conservation of linear momentum to solve this type of problems. And the third one, which is also important, in order to consider this, we first need to highlight one thing. We mentioned that linear momentum is a vector. That's why, let's say, we have two-dimensional space. there is some vector p. So it is true like p1 and then some vector p2, because let's say we have system of two bodies. So here will be some vector p2. So we have shown already for a closed system or quasi-closed system, p1 vector plus p2 vector is equal to constant. So that is also true for the projections, like sum of projections of these vectors on axis x and axis y. So here we can write that p1x plus p2x is equal constant, and p1y plus p2y is equal constant. So technically, this part is just another form of this part. So it's just written in vector form. So taking this into account, taking this into our mind, we can consider such situation when in this two-dimensional space, x, y, we have some force, F, acting on the external, external force acting on this system. So in this case, by definition, so it's net external force which acts on the system of bodies from outside. So that is, and this net force is not equal to zero. So that by definition is already not closed system or quasi-closed system, because this force is net force, means it's not compensated by some other forces. However, here matters its orientation. We see that the projection of this force on axis y is equal to zero because it's perpendicular to axis y. It's along axis x. So in this particular case, we can write that p1x, like projections of these vectors of linear momentums on axis x plus p2x will not be constant anymore, because specifically in this direction of axis x, the condition for a quasi-closed system is not valid anymore. There is some net external force. So we cannot apply this concept of conservation of linear momentum. However, since the projection of this external force on axis y is equal to zero, we can still write that p1y plus p2y is still constant, and this still follows the conservation of linear momentum. So it can be useful even for the systems which are not by definition closed, but depends on the orientation of external force, or depends how we build the frame of references, our coordinates x and y with respect to this external net force. We can still apply for one of the direction this law of conservation of linear momentum. So this is very important and can be quite helpful for some particular cases. So with this, I think we introduced all concepts of linear momentum, its conservation, and different cases, like situations when it can be applied. So either like first one is quasi-closed system and all forces external are compensated. Second, when external forces are much smaller than internal. And the third one, when we have zero projection of external force on one of the axes, then along this axis, it's possible to apply conservation of momentum for the projections of linear momentum vectors on this particular axis. So now let us consider some cases of collisions, like different types of collisions between bodies, and that is elastic. So in this case, when we have elastic collision, both conservation of linear momentum and conservation of kinetic energy can be applied, because we don't have any deformation of the bodies which are interacting with each other. And that's why we can also consider that kinetic energy conserved. The other one is like other extreme example is perfectly inelastic. So in this case, two bodies literally stick to each other during interaction, and they start to move after collision as a single body with mass twice large. Like mass is defined by the sum of masses of two bodies before collision. In this case, we cannot apply any more conservation of kinetic energy. The explanation for that is because part of kinetic energy is transformed into internal energy, which is associated with the deformation of these bodies and heating them up because of this deformation. And however, at the same time, we can still apply this concept of linear momentum conservation. And the third type, which is something in between, it's just called inelastic. And for inelastic, these bodies don't stick to each other. They are detached after this moment of collision. However, these bodies still experience certain deformation. That deformation converts part of kinetic energy prior the collision event into internal energy of these bodies. So they kind of warm up. And that's why conservation of kinetic energy is not applicable. However, conservation of linear momentum also is applied. So we will consider like examples of perfectly inelastic and then elastic collisions as some extreme cases. So let me go to another slide, and let's first consider perfectly inelastic collision. So let's assume we have some axis X, and we have body M1, body M2. So this body M1 is moving along axis X with velocity V1. This body M2 is moving with velocity v2 in opposite direction. So at some moment, these bodies will collide. And then, since it is perfectly inelastic collision, they will stick to each other. And let's consider that they will move with some velocity v as one body already along axis x. So in this case, we need to consider this linear momentum conservation. So we have m1 times v1 as positive because this momentum is aligned along axis x. Then we have minus m2 times v2 because linear momentum of this body m2 is aligned in the opposite direction in to the axis x, and eventually we will get some after collision, the momentum of whole system will be m1 plus m2 because they stick together times v. So we get it now positive because we assume that this linear momentum after collision will be along axis x. But we will discuss this case a bit later. So from here, we can easily get the velocity of the attached system of these two bodies after collision. And this will be m1 times v1 minus m2 times v2 divided by the sum of these masses, m1 plus m2. Here, if m1 times v1 means the linear momentum of first body is larger than the linear momentum of the second body aligned in opposite direction, then this v will be positive. However, if it is in the contrary, if this linear momentum of the second body is larger, we see from equation that v will be smaller than 0, will be negative, and means in that case it will be aligned like this. So our initial assumption of the direction of motion of this attached system of two bodies after collision was wrong, and the true direction of the motion and also direction of the linear momentum vector will be in the opposite, like pointed out in the opposite way. Okay, I think that for today, this is what I wanted to tell you. We introduced the concept of linear momentum, have shown how linear momentum is, the change of linear momentum is related to the change of to the impulse of the applied force to the system. Then have shown that for the closed system or quasi-closed system, there is conservation of linear momentum, means it doesn't change the sum of all linear momentum vectors of this closed system before and after collision remains constant, and considered like 3 different types of collision in the elastic, inelastic, and perfectly inelastic. So we in details discuss this perfectly inelastic collision, and then on the we will continue with discussing elastic collision on Wednesday and proceed further within the scope of this topic with this discussion of other concepts which are very important and useful for application in solving different problems. Okay, thank you very much for attention. If you have any questions, you're welcome.
Thank you. Goodbye.
Yeah, if not, then thank you for attention.
Okay, thank you, teacher.
Thank you. Goodbye.
And
Thank you.
Thank you.
Goodbye.
Bye.
yeah, take care.
Goodbye.
Have a good evening and see you on Wednesday. Bye-bye.
You, Dr. Brus. Bye.
Thank you.
Bye.
Good lecture. Goodbye.